Whoops. Let's go back to where we started from. Okay, so this is a program on urine formation. I'm going to talk more about the structures of the nephron, the glomerulus, the corpuscle or uh, the capsule around the nephron, the proximal and distal convoluted tubulars, and then the capillaries and things like that. We're also going to talk a little bit about the control of urine formation. So, just a quick review. Last time I introduced the system, the urinary system, that functions to get rid of waste products like nitrogen wastes and acids and things like that. This system plays a big role in regulation, homeostasis, regulating blood pressure, blood volume, um, the amount of water, the amount of sodium, calcium, chloride, things like that. It also plays a role in regulating pH and producing red blood cells. The kidneys are big drivers of metabolism. Okay, most notably is they metabolize vitamin D to an active form, and they used are used to modify and excrete lots of substances. Okay, and I showed this one. This slide here showed the concentration of materials in urine and how much urine is produced per day, somewhere around 1.5 liters. We don't lose good things in urine, but we get rid of things like nitrogenous waste like urea, uric acid, and creatine. We can also adjust concentrations of other things like ions like sodium, potassium, chloride, and bicarbonate. Okay, so the kidney is the organ that does this. It's a very vascular organ, has a large amount of arteries coming to it that will divide up, and they're located kind of on the back of the abdominal cavity. The real active part of the kidney is the nephron. The nephron is a capsule that surrounds a blood vessel called the glomerulus, and then wastes that are collected from there are modified in these tubules. There's the proximal convoluted tubule, the nephron loop or loop of Henle, and then the distal tubule and the collecting duct. These glomeruli are located in the outer region, the cortex, okay, and most of the proximal and distal tubules are right on this edge of the cortex, and then the nephron loops go down. Okay, so then I introduced urine formation, which was three things: filtration at the glomerulus, okay, then tubular reabsorption of things from the filtrate to put back into the blood, which happens primarily in the peritubular capillaries, and to a lesser extent in the nephron loop and some of the other parts of the nephron, and then tubular secretion. And so we're going to go through those in just a little more detail today. So first, the glomerulus, what happens at the glomerulus? And so glomerular filtration is something that happens at this glomerulus. It's this blood vessel that's kind of a leaky capillary. It's kind of one of these sinusoid capillaries. And so small molecules like water, salts, sugars, amino acids are small enough to pass through this lining of the glomerulus. And then that means they're going to enter the nephron in this corpuscle here, or the capsule, and then start on their journey down the nephron. The rate that this happens is called the glomerular filtration rate, and that depends upon blood pressure. Okay, so you need a certain amount of blood pressure to force materials through the capillaries, and it has to be high enough to overcome the blood's tendency to hold on to fluids by osmosis and to hold on against back pressure from fluid in the capsule. Okay, and so below a certain blood pressure, we really can't filter. But we can measure this pressure. We filter about 1 liter, or we filter about 1 liter of blood per day. That's something like 20, or per minute, 1 liter per minute. That's 21% of cardiac output. And generally that leads to the filtrate being formed at a rate of about 125 milliliters per minute. Per day, that means about 180 liters of filtrate are formed. But that's filtrate right here. Almost all of that is going to be reabsorbed. Okay, there'll only be about 1.5 liters of urine made. So, 178.5 liters will be reabsorbed. Okay, so that's filtration at the glomerulus, and that's just size separation. Small things can pass through the glomerulus. Now, blood cells can't, white blood cells can't, proteins shouldn't be passing through. And so those are the things that shouldn't be. But once those things leave, then the filtrate has to be modified. And so here, the first column shows the filtrate, okay, and the filtrate, again, 180 liters per day. And then there's the number of grams that pass through for proteins, chlorine, sodium, bicarbonate. And then it shows you the amount reabsorbed. Okay, and so for a lot of things, virtually all of it's reabsorbed. For glucose, it should be all of it, almost all of it. For chlorine, almost all of it. For sodium, almost all of it. For bicarbonate, almost all of it is reabsorbed. Okay, and so where does this happen? Well, most of this happens in the proximal convoluted tubule. Okay, particularly glucose, amino acids, we want to get those back right away. And so here, the purple boxes show you reabsorption and where it happens. So this is the proximal convoluted tubule. Here's the distal convoluted tubule. Here's the descending part of the nephron loop. Here's the ascending part. And then this structure here is the collecting duct, and it shows you that we're doing some reabsorption there. It also, I should mention here in these yellow boxes, this is secretion into the tubes. And so we're secreting some things from the blood into these tubes. That includes urea, uric acid, creatine, drugs, acids, hydrogen ions, that's acids. Ammonium is in there. Potassium are things we secrete in there. And so those are things that are secreted. But reabsorption is the key thing here, because that's how we get the good things that are filtered back. Okay, and this is, how does this happen? Well, that's a question. In most cases, there are specific proteins in the walls of the cells lining the proximal convoluted tubules. And so you see here on the left side, it shows these little transporters here. And some of these are active transport, where we use a molecule of ATP to bring something back. Some are symport, where we again use ATP, but now we bring two molecules back. We bring the sodium back, and the negative chloride ion follows. In other cases, we're secreting things, or diffusion and osmosis can help us bring things back. But probably the first two are the big ones. And so proximal convoluted tubule, this is the most active part. These cells lining the nephron are actively doing this stuff back, and it's going into the bloodstream. It's going into the paratubular capillaries. Okay, in the nephron loop, there's kind of an interesting thing going down. Remember, the nephron loop goes way down into the renal pyramid and the renal medulla. And here, we form what's called a countercurrent multiplier. And so as things go down in this loop, water tends to move out by diffusion. Okay, and as water moves out, urea is going to move in. And so there's transport of these things going on. But then in the upper loop, you are actively transporting sodium reabsorbed out. And so as water, this water is going back into the blood, and then the sodium causes the accumulation of a high concentration of salts in the deeper part of the kidney. And this is what draws the water out over here. And so this is called a countercurrent multiplier, because you set up this deep concentration gradient of solutes that's helping to pull water out. And so you can more and more pull water out, and just by osmosis, and then you put blood vessels right nearby, and so those things are going to go into blood vessels. And then in addition, this is going to go back up into the distal convoluted tubule, kind of shown here. And here there's again some active reabsorption. And then as it goes down the collecting duct, it goes back down into the renal medulla. And depending on the permeability of the collecting duct, as it goes down into this salty region of the kidney, the medulla, it can reabsorb water. You can make the final reabsorption. And so this goes on right there. Let's see, what else do I want to talk about here? Urine regulation. Okay, I've mentioned these hormonal molecules that do this. Okay, we're going to go through those in a little more detail. And the key structure here is this juxtaglomerular apparatus, which you can see in the upper left-hand side there. It kind of shows it on the other side, but this is where the cells of the distal convoluted tubule are lining up next to the afferent arteriole. And they sense the blood coming through that afferent arteriole, and some of these cells are secreting hormones. For instance, if they sense a low amount of blood pressure, the kidney, those cells will release the enzyme renin. And renin will work on a blood protein that's released by the liver called angiotensinogen. And renin will convert that to angiotensin 2, or angiotensin 1, and then that's converted to angiotensin 2 in the lungs. Okay, and aldosterone, this mechanism of aldosterone, is what's going to increase the production of aldosterone. So renin angiotensin leads to aldosterone. That causes the kidneys to increase sodium and water reabsorption, and this will increase blood volume and blood pressure. Angiotensin 2 is also a vasoconstrictor that will also secrete blood pressure. This is the major mechanism that we have for dealing with these blood pressure and blood volume. Another important hormone that I mentioned is, I'm not going to show in more detail, and that's antidiuretic hormone, ADH. Okay, and thirst centers in the hypothalamus are close to osmoreceptors that detect how salty or how watery is the blood. And that triggers thirst, but it also triggers the hypothalamus to cause the pituitary gland to release antidiuretic hormone. Okay, that works on the collecting duct, and it causes that duct to be more permeable as it goes down through the medulla. So that increases water reabsorption, and it helps us to make a more concentrated urine if there's not enough water in the blood. Okay, and so this is here's the molecule ADH binding to a receptor on the cell of the collecting duct, and that causes the collecting duct to make more aquaporins, which allow for water reabsorption. So this is kind of similar to angiotensin in that it's going to increase water reabsorption. So that's going to help boost blood pressure and blood volume. Okay, and the last one we're going to go over is atrial natriuretic peptide or protein. And this is released by the heart whenever there's a lot of stretching, like when you have high blood pressure and high blood return. This hormone, one of its main effects is that it's going to increase excretion of sodium ions and water. And so that will lower blood pressure. So it's an antagonist to the other two hormones. Okay, so we'll stop